All right, in section 6.2, we move into finding volumes by integrating instead of just areas. So this problem asks us to find the volume of the solid obtained by rotating the region, this is yellow shaded region, bounded by x equals negative y squared plus 3, the red parabola, and x equals 2, the green line. So this is a region, and we're going to rotate that around the x equals 2 axis. So I will draw in a little arrow around the axis to indicate that we're rotating around that. Now, before we really start to work on how to solve this problem, let's remind ourselves of a couple of things we know. One of the things that we know from 6.1 is that if our goal here were to find the area of this yellow region, we would want to start by drawing a picture, we've done that, and then looking at the representative rectangle that shows us which direction we're integrating. And if you remember here, if we set a representative rectangle up and down, we run into the problem that the same function is bounding us on top and bottom. And when we subtract those to get the height of the rectangle, you have f of x minus f of x, and they cancel each other out. That's no good. So let's undo that. We don't want those rectangles. Instead, this is a good example of a problem where we want our representative rectangle to be sideways, and if we were finding the area of this, we would integrate with respect to y, where the width of this little rectangle is delta y, and then as we shrink it infinitesimally small, we would say that is dy, our differential. And we would integrate from, our little rectangles go from here to here. At some point we'll want to find out the coordinates of those points of intersection. And then we would, integrating would give us the sum of a bunch of those rectangles and the limit as they got infinitely skinny. All right, but we're not doing areas now. We are looking at volumes of solids. So let's see how volumes are related to areas by going back to geometry. And remember back in the day when we wanted to figure out the area of a rectangular prism. We'll actually use a square prism here as it's even easier to draw. The idea is if I just knew what the cross sections of a prism look like, then I can take the area of the base and multiply it by the height to give me the volume. So for a rectangular prism, we have length times width gives you the area of the base, and then times height to give you the volume. Or another prism that you're probably familiar with is a cylinder, where the volume of the cylinder is the area of the base, which is pi r squared, times the height, where our height is like this and our radius is like this. And sometimes our cylinders are tall and skinny, and sometimes they're very short and flat, but even coins can be cylinders, right? Very small height and a larger radius. So let's go back up to this problem and think about this yellow region. If we were to rotate it around the x equal 2 axis, the green axis here, what's going to happen? Well, this red curve is going to sweep out, and when it comes around flat again in the plane, it's going to look reflected over there, and as it goes around and around, it's going to sweep out a circle, and we're going to get a football-shaped three-dimensional object. Okay, so the volume swept out by this yellow region is a football-shaped solid that if you look at any little cross-sectional area, you get a tiny little disc or coin that has a width delta y. What would the radius of that disc be? Well, the radius is whatever the distance is here, the x distance. So how do I find out that x distance? Well, my axis is all the way over here. Here's 0, 0. The x distance for this representative rectangle is whatever this point is in the x direction minus whatever this point is in the x direction. And to figure those out, I need to go back to my functions, x equals negative y squared plus 3 and x equals 2. So the radius of a single disk in this picture is the red function, negative y squared plus 3, minus the green function, 2, the difference between those. Sometimes you have one called f and the other called g. This would be f of y and g of y. All right, I'm going to pick up that work. I wish I had done it over here, so I'm just going to pick it up and move it. The nice thing about working on a computer. Go back to my pencil tool. Okay, that's the radius of a single disk. So how do I figure out the area of a single disk? Well, that's pi r squared. So what's my radius? I've got negative y squared plus 3 minus 2, and I'm squaring that. That gives me the area of a single disk. And if I want to know what's the volume of one of these disks, one of these really short cylinders, I have this pi r negative y squared. Let's go ahead and do plus 3 minus 2 is just plus 1 squared times, well, the height of that disk we said was delta y. And if I want to add up a whole bunch of these, the sum of the disks, the sum of these pi r squared delta y, remember that's exactly what it means to integrate. The integration is taking the limit of this sum, so my volume is going to be the integral from a to b, we haven't figured those out yet, of pi r, which is negative y squared plus 1, squared dy. Okay, so let's go back and figure out what our bounds of integration are. For that I need to know, in this picture, the y values range from what to what. Okay, so can't see the picture. Let's see if we can keep it. I want to know, where does the red curve intersect the green line? So the green line is x equals 1. The red curve is x equals negative y squared plus 3. I want to know what these have in common. Set them equal to each other. So 1 equals negative y squared plus 3. Subtract 3 from both sides. Oh, it's not x equals 1, it's x equals 2. That's going to make my math actually a lot easier. So 2 is negative y squared plus 3. Subtract 3, I get negative 1, and so y squared equals 1, or y is plus or minus 1. So we really want to be integrating now from negative 1 to positive 1. And now we have set up this problem, the volume, and this is what we call the disk method because we're using a bunch of disks stacked on top of each other to represent the volume, and we get that it's the integral from negative 1 to 1 of pi negative y squared plus 1 squared dy. I'm going to leave the solving of that integral to you because we've done this in chapter 5 a lot, and that's not a terribly hard integral. Take your pi out and then FOIL it out and you have a polynomial to integrate. Plug in your bounds and you're done. Before we leave this problem, before we move on from this problem, I want to consider something similar but a little bit different. I'm drawing in a representative rectangle in the same region. So the difference here is we want to consider, what if instead we rotated about the axis x equals negative 1? So something that's far away from the region. And then if you think about, as this thing sweeps out and creates this shape on this side, oh, that's pretty bad. Let's see if I can clean that up. Shape on this side, that's supposed to be this yellow region reflected over here. The rectangle swings around, and instead of carving out a disk in space, it has a big gap in the middle, this gap between the inner radius and the axis of revolution. There's a gap between the axis and the yellow region, so it creates a big circular gap around the axis. And you get this shape that kind of looks like a bead or a ring with a big gap in the middle. All right, so instead of these cross-sectional disks that we're used to with maybe a radius and a height, delta y. Instead, we have a cutout out of the middle. So how do you find the area of a washer shape? Well, you take the area of the outer circle minus the area of the inner circle, and then to do the volume, just multiply by your delta y. So here in this picture, I'm going to need to find my outer radius, and that is the radius from here all the way back to my axis of rotation, not to the y-axis, but my outer radius is going to be here. And so that is -1. So from here to here is -1. And from here to here is my function, which is x equals -y² plus 3. So I have -y² plus 3 minus -1, or plus 1, to give me that full distance. So the capital R, the outer radius, in this case is -y² plus 3 minus -1. That's the axis of rotation. And so I get -y² plus 5. The inner radius, little r, in this case, since it comes from this line x equals 2, the inner radius is always fixed. The inner radius always goes from here to here. So 2 minus -1. Here's the 2, here's the 1. It's always going to be 3. And then how do we figure the area? Or let's just skip ahead to the volume. The volume is going to be the integral. You're going to have pi outer radius squared, -y² plus 5. That's pi r squared gives you the outer circle, minus pi inner radius squared. And then, because it's a volume and not just an area, we have a dy for our thickness of our disks. And what did we say our bounds were for that yellow region? We said it went from -1 to +1, so it's the same bounds here. All right, so disk method, washer method. It's called the washer method if your disks have a hole in it. If your representative rectangle is set up sideways, you're integrating with respect to y. It is possible to work these with respect to x, and I think we have another video.